Okay, good. So welcome everyone. So today it's my pleasure to welcome Jason Bramburger, who will be talking about deep learning of conjugate mappings. Yeah, thank you, Jason.
Okay, so thank you very much for having me, Bhumajan. It's going to be my pleasure to share with you some work that I've been doing over the past couple of years. So a lot of the foundations for this were put forth in a paper that was now published in Physica D last year with my two advisors at the time. That's Steve Brunton and Nathan Coots. And then I'm hoping to show you a little bit of the ongoing work towards the end, where I hope to take this and some of the stuff that I'm actively sort of writing up at the moment. Okay, so let me begin by maybe setting the stage for what it is that I'm interested in. So going, all the way back to my undergraduate career, I kind of became obsessed with chaos theory. I just thought it was the coolest thing in the entire world, and I wanted to at some point, find a way to sort of tailor my research to it. And what I like about chaos theory is it looks so complicated, right? So for example, I have the Lorentz butterfly attractor shown for you on the left-hand side here. And you can see a point sort of winding along this trajectory according to the vector field or the flow of the vector field. And, one of the things that the mathematicians really got right about chaos theory is that naming it chaotic is a fairly apt name. In particular, this looks very complex. It looks unpredictable. It looks like there's a sort of random element here where you're switching between these two lobes. But fortunately for us, decades of mathematical research has shown us that there's a lot more going on here than meets the eye. And in particular, there is a structure in chaotic systems. And that structure comes in the form of infinitely many unstable periodic orbits that densely fill up this chaotic attractor. And these things are, as I said, unstable. So what you can really think about is the motion winding along this chaotic attractor as maybe starting close to one of these periodic orbits. And because it's unstable, you can only stay close to it for so long before you're pushed away. And then you sort of jump to the neighborhood of another one of these periodic orbits, and you continue this sort of random jumping back and forth between all of these infinitely many periodic orbits. Now, this is a sort of geometrical perspective, but from a mathematical or an analytical perspective here, we have all kinds of nice results that show us that a lot of the things that we care about when it comes to a chaotic system, so things like time averages of observables or invariant measures, these things can be computed exactly just by knowing these periodic orbits that densely fill up the attractor. So really the idea here is, if we take a chaotic system, how is it that we can extract this important information? And the answer comes from finding the unstable periodic orbits. Okay, so if I would like to go forward here, I'm going to have to go backward. And I'm going to have to go way back to the late 1800s, to the work of my favorite mathematician, and that is Henri Poincaré. Now, for a little bit of history here, back in the 1890s or so, Henri Poincaré was working on a version of the three-body problem. And what he found is sort of a sort of classic story now in mathematics, that he observed the first sort of chaos taking place in this three-body problem. Now, of course, this is the 1890s, and Poincaré doesn't have, say, a computer to help do his simulations for him, but he doesn't even have most of the mathematical tools that we just have at our disposal now, right? Things like well-developed theories of topology, for example. But what makes me really love Poincaré is he, despite all of these challenges facing him when it comes to analyzing a chaotic system, he sort of persevered and he pioneered one of the main approaches that we have for understanding these chaotic systems. And in particular, what he noticed is that, even though these things aren't periodic, these systems, because if they were periodic, they would be predictable, they would not be chaotic. They are what's called recurrent. That means that they always sort of come back to the same region of space. And What Poincaré had the foresight to do is introduce a lower dimensional transverse to the flow subsection in some recurrent region of space and simply track the intersection of these continuous time trajectories every time they pierce through this subsection. Now, this subsection is typically called a Poincaré section now. And you can imagine sort of collecting up intersections from a single trajectory in this Poincaré section. And you can theoretically think about a mapping which will tell you, if you hit right here, then you are going to hit, say, here at your next spot. So this mapping that theoretically iterates you through successive intersections of this Poincaré section is now named after the person who came up with it, right? This is a Poincaré mapping. Now, Poincaré mappings, despite being a very old idea in chaos theory, are still tremendously valuable. So one thing that we get from them is we get a sort of slight dimensionality reduction. And this just comes from the fact that you're moving from a continuous time system to a discrete time system, right? So your phase space is inherently lower dimensional because it's just a piece of this full continuous time phase space. But of course, this isn't the real advantage here. The real advantage is that it's through these discrete time iterative processes, so these Poincaré mappings, that we have all of our understanding of chaotic systems. So if you took a class on chaos theory in your undergrad or in your grad school, you probably spent all of your time talking about discrete mappings, right? Because this is where we have developed up much of our understanding here. And in particular, we know that those unstable periodic orbits from the previous slide, well, they manifest themselves as recurrent or periodic trajectories in this Poincaré map, right? It's just a discrete sequence of points that eventually repeats after being iterated through this mapping. So of course, what's the problem with this? Well, the problem is that, if I give you a specific system, it is almost impossible for you to just say, okay, here's the associated Poincaré map. So, even though it works really, really well in theory, most of the time we limit ourselves to very simple mappings where we can get some phenomenological description. And this has really sort of been where a lot of my work has been focused around. It's sort of bridging this gap between a specific system that you want to work on and all of the theory that we've developed up for these Poincaré mappings. So in particular, I've been using model discovery algorithms in order to identify some of these Poincaré maps. Now, let me just briefly show you, so let me show you how it is that I want to approach this. This skipped a slide, pardon me. Okay, sorry. Let me just briefly introduce you to how it is that I've been approaching this in the past, because this is going to influence how it is that I've been working through some new ideas here. And in particular, what I've been using is the so-called SIND method. So this stands for the sparse identification of nonlinear dynamics. This came from two of my advisors, Brenton and Coots, along with another collaborator, Proctor, from a really, really highly influential 2016 paper. And the beauty of the SIND method is that it is fantastically simple. It is, very easy to implement on a computer, and it is very practical for obtaining, say, these Poincaré mappings. So the basic idea here is you integrate up your system that you might be interested in. You then proceed to define a Poincaré section, and you start collecting successive iterates or successive intersections of your continuous time dynamics with this Poincaré section. So the result would be a collection of data points, say x1, x2, x3, and so on and so forth. And then what you can do is you can arrange these this data into two huge data matrices. So I've called them capital X1 and capital X2. And the basic idea here is that each row of these data matrices is mapped into the corresponding row of X2, for example, by your unknown Poincaré mapping. So it's a row-wise transformation of this Poincaré map. Then what the SIND method asks you to do is it says, okay, imagine that you can expand your unknown function f in a basis, right? So for example, here I'm just using a little Taylor expansion, but maybe you like using Fourier terms or Legendre polynomials. It's entirely up to you. You can mix and match as well. This is a library-based method. But essentially what this means now is that you are left to tune the coefficients in your library expansion in order to best fit the data that you've been given. And you can alternatively pose this thing as a massively overdetermined linear algebra problem, where the unknowns of your linear algebra problem are now those coefficients that appear linearly in your basis expansion. Now, this is not something that we have any real difficulty solving, right? This is essentially a one-line MATLAB routine where you can find, say, the least squares solution along this. But what the Cindy method does is it actually uses an Occam's razor type argument. And it says, okay, maybe you can give me the least squares solution here, but I would like the mapping that might sacrifice some accuracy for interpretability. So that is, I want the one that uses the fewest library elements. I want a sparse solution here. Now, this is a little bit more complicated because this becomes a non-convex optimization problem. But what the Cindy method does is it relaxes this problem into something that is very easy to implement. Basically, what you do is you solve for the least squares solution. Then you implement a thresholding routine. You scan through your solutions, and if they are smaller in absolute value than your threshold, you eliminate the corresponding elements from your library, and then you repeat the process with your smaller library and your function expanded in a smaller basis until you eventually arrive at a model that cannot be sparsified anymore. So again, this is what I've been using, or what I was using for a while, but unfortunately it comes with a few limitations. The first of which is that it is very, very sensitive to your basis expansion when you're dealing with chaotic data. So this is a version of sensitive dependence on parameters for these chaotic systems. But essentially, if you don't have the exact right components on in your library or in your basis expansion, you're just not going to be able to do a good job fitting that data when it's chaotic. Chaotic data is very specific to the system that it is governed by. And so this sort of leads to the natural question most people have for me. And they say, what do I use for my basis? What should I be using, especially if I'm using chaotic data? And unfortunately, no one has really come up with a good answer for this. Nobody has been able to say, well, you should use polynomials if this, or Legendre polynomials, or Fourier terms if this. Unfortunately, we do not have a prescription. The sort of common refrain that people say is the more functions, the better, but good luck. So what I decided to do is I decided to turn this discovery process on its head and look back to some very old ideas coming from the world of topology. And what I wanted to do is implement the idea of a topological conjugacy to create a sort of version of indirect discovery of Poincaré mappings. So let me lay out the theory for you first, and then I'll talk about how we implement this computationally. The basic idea of a topological conjugacy is that, say we have some mapping F, that might be my unknown Poincaré mapping, that takes a space X back into itself. Well, a topological conjugacy generates a commutative diagram between say a mapping F and another mapping G from another space Y back into itself, where the topological conjugacy is this function X that transforms the domain and range of F into the domain and range of G while respecting this little equality that I have for you at the bottom. Now, essentially what that equality means is it says that if you would like to iterate through the dynamics of F, then what you could do alternatively is transform the space with H, then push forward with the mapping G, and then transform the space back with the inverse of h, right? So instead of going from the top left to the top right of my diagram, you can go down, bottom left, bottom right, up. Now, I'm going to do a little bit of mind reading here for a second because I can probably hear your thoughts through the screen. You are thinking to yourself, Jason, you just told me on the last slide that discovering one map was a bit of a pain, right? I tried to communicate to you that with the Cindy method, but now you're telling me, Jason, that you want to find two mappings, G and H potentially, and one of them has to be invertible on top of that, right? So now you have a lot more specificity in terms of what it is that you want to do and how you want to get there. Well, before I try to convince you that this is doable, let me convince you that it's a good idea, at least on paper. So here's the basic premise. The purpose that people use topological conjugacies, again, especially if you took a chaos theory class in your undergrad, you've potentially seen these before. This is really how we relate what could be potentially very complex systems to ones that are simpler. So typically when you are introduced to topological conjugacies, you are faced with this example right afterwards. And so what you have here is you have a mapping f of x, which is a piecewise linear mapping. So this is referred to as the tent mapping. So if you just sketch it out on a piece of paper right beside you, it just looks like a little triangle or a nice little tent. Now, what we know about the tent mapping is that through this complicated conjugacy function h, this arc sine of the square root of x, what that does is that transforms the dynamics of f into a simple little polynomial mapping. That is your standard logistic map, g of y. Now, here's what you might be thinking. If I can continue my mind reading routine here, you might be thinking to yourself, well, Jason, piecewise linear seems a lot better than polynomial. Piecewise linear is very, very easy to work with. And there's a whole theory, like John Milner and his associates and his collaborators have developed these massive theories about piecewise linear mappings. But here's the problem. Think about this from a model discovery standpoint. So in the Cindy method, if I give you data gathered from F, so this piecewise linear mapping, how difficult do you think it's going to be to try and discover that thing using a library of basis functions? It's probably going to be pretty hard because I'm willing to bet that you are not creative enough to put in piecewise linear functions, especially where do you break up the piecewise linearity? But here's the reward. The idea here is that if you can find that complicated function h, then the discovery process for the function g is relatively easy. This is discovering, a Taylor expansion essentially. And this is something I can do. Again, I'm not very creative. I would prefer to stick with polynomials if I have the opportunity. So this is the basic premise of everything that's going to lie underneath what I'm going to talk about for the rest of this talk. And what I'm going to show you now is how we can implement this using modern neural network architectures. So here what I'm showing you is what's referred to as an autoencoder neural network structure. So before you start becoming potentially overwhelmed with the nuts and bolts of this thing, let me just show you, let's just focus on the input and the output, okay? So maybe cover up the middle of the screen. Just look at what goes in and what goes out. The idea here is that the neural network mimics the unknown, say, Poincaré mapping. So if you gather data and you know that your data pushes, your unknown Poincaré mapping pushes xn forward to xn plus 1, that is what the neural network is doing. It takes in xn and it spits out xn plus 1. But now if you uncover your screen, you can see the nuts and bolts of how this works. The way that this works is mimicking that conjugacy diagram from the previous slide. And in particular, what happens is you feed your data xn in, and it gets processed through a conjugacy. So that's your encoder function, if you're more familiar with this, with autoencoders than you are with topological conjugacies. Then inside of the neural network, you have a Cindy-type discovery process that discovers a conjugate mapping G simultaneously during the training process of the encoder and decoder architecture. And once you push forward your conjugated data inside of the neural network, then you undo the conjugacy, undo the change of variable, and pull yourself up back to the observable Poincaré section space. Now, this has a number of advantages for the discovery of chaotic mappings. So first of all, if you are familiar with autoencoders, you are probably familiar with them because of their dimensionality reduction abilities. Now, this is typically used for mapping, say, pictures down into low-dimensional feature spaces, but you can actually take advantage of this idea for my neural network architecture given on the board here, because you can imagine that I'm collecting data from a very high-dimensional system, but that data is really only describing, say, a low-dimensional chaotic attractor. So for example, maybe I have 100-dimensional data, but really there's just a 1 or 2-dimensional structure in there. Well, then what the neural network can do is it can project you down onto a lower dimensional manifold while simultaneously finding a change of variable, so a conjugacy function, on that lower dimensional manifold to best fit a conjugate mapping G. Now, a sort of corollary of this is that you get improved accuracy for forecasting because you're just doing a better job of fitting your data. So that's something I'm going to try and show you in a moment with some of the examples that I have coming up. But really, the advantage here is that this lifts a lot of the burden of choosing the dictionary that you're going to try and discover that conjugate mapping G in. In particular, maybe like me, you like using polynomials. And so you can expand G simply in a polynomial basis, and you can force the encoder and decoder functions to do the hard job of transforming the data so that they can actually be fit by a polynomial. Now you're not as much doing a guessing game. You're forcing the neural network to sort of abide by your own standards. And then for me, the real thing that is great about this is that these topological conjugacies that I showed you on the previous slide, they basically preserve all of the dynamics of a system. So things like topological entropy are preserved. We know that, for example, orbits are mapped in a one-to-one correspondence between, say, F and G, your conjugate mappings. And what this means is that if I wanted to find periodic points of my Poincaré mapping, right? Remember, these things correspond to those unstable periodic orbits that I cared about so much at the beginning. Well, what I could do is I could mine the periodic points out of my simple conjugate mapping G, right? This is something I can sit down with pencil and paper and just work through. And then I can use my decoder, or the inverse of my conjugacy, H inverse, to lift those points back up to the corresponding intersections of the unstable periodic orbit with the Poincaré section in the observed space, right, in the XN data set. So this gives me a way of sort of systematically and accurately mining out my unstable periodic orbits. Now, I just want to briefly address something. The first strength that I have written here is a dimensionality reduction. Now, a lot of time when people are training, say, autoencoders, if you want to, say, find characteristics of given, say, images or something like that, you typically have to vary the dimension that you're going down to. However, you can actually do this in a very systematic way. You can actually figure out what the dimension you should be projecting down to is based again on a lot of well-developed mathematical theory. And this theory comes from the idea of Lyapunov exponents. Now, Lyapunov exponents, as you can see from this sort of illustration on the board, are characterizing the fundamental characteristic of a chaotic system. That is the sensitive dependence on initial conditions. 2 points that start very close together are going to exponentially separate. And these Lyapunov exponents are characterizing that exponential separation. Okay, so we typically represent a chaotic system, or we understand a chaotic system to have at least one positive Lyapunov exponent. And this led to Kaplan and York creating a famous conjecture that the Hausdorff dimension of your chaotic attractor is given essentially in terms of the number of positive Lyapunov exponents plus some little non-integer part. Now, what this means is that you can use that Kaplan-York dimension to identify the dimension of your latent mapping, right? So this can help you to boil out any any redundancies in your data and pull yourself down to a finite dimensional, low dimensional system. I see there's some questions. I can try and answer them.
Yeah, there are some comments from
Yeah, thanks. No, I'm interested to know, you're talking about topological conjugacy, but particularly if you're going to go to Lyapunov exponents, then you probably really want differentiable conjugacy. So what sort of smoothness properties do your neural nets make for H?
Yeah. So I'm using typically CellU activation functions. So these are in fact smooth activation functions. And okay. So essentially, everything with the mathematical theory is approximate, right? So essentially, I'm piggybacking off the idea that smooth functions are dense in the set of continuous functions, right? So conjugacies only need to be continuous, but I can approximate those using a smooth function, for example. So I'm sort of sweeping a lot of this theory in under the rug for the sake of the talk, but that is sort of what I'm relying on here with my neural networks.
Okay.
So, sorry, I have another question regarding the conjugacy, if I can.
Sure.
Okay. My doubt is the dimension is a topological invariant, right? So if your H is smooth and you reduce the dimension, it means that basically H minus 1 must be discontinuous, right?
Well, yes. So again, I'm sweeping some details under the rug here, but the idea here is you're only sampling from the chaotic attractor, right? So for example, you could describe a circle in 5 dimensions, right? Sine of t, cos of t, sine of t, cos of t, sine of t, right? But that's really only describing a one-dimensional object, right? So you project yourself down onto the circle. You leave the other 4 dimensions alone because they are not part of, say, the chaotic attractor. So the assumption here is that with your training data, sorry, let me try and find this. With your training data xn that's being put in, it's only coming from the chaotic attractor. There's no transient data that's being used, and therefore you're only making observations on a low dimensional manifold potentially.
Okay, so it's a sort of diffeomorphism onto the image, right?
Yeah. So you're using the, yeah, exactly. Actually, it is exactly that. Yeah.
Okay. Thank you so much.
No, thank you. I appreciate both of the questions. I mean, this is good. Okay, yeah. So now I've given you a lot of theory. I mean, now we can do the fun part. We can actually just talk through some applications of this. And I want to show you, where this works and how it can work and how it can help you. And I know that everybody's favorite toy model in all of chaotic systems is the Lorentz system. And don't worry, I'm going to talk about the Lorentz system, right? I wouldn't show you the butterfly at the beginning without talking about it. But if I do one thing in my mathematical career, and if that is to convince people that the Rössler system is way more fun and just way cooler, then I will die a very happy man. I truly love the Rössler system, and so this is where I want to start. So like the Lorentz system, the Rössler system is a very, very simple three-dimensional ordinary differential equation. This is, sort of your prototypical chaotic system where the chaotic attractor I'm showing you in white here. This thing is essentially a Mobius band. It's just like, just take a piece of gum and stretch it and then fold it back over itself, and you'll basically create this thing. But what I really love about the Rössler system is essentially it's an excellent testing ground for a lot of understanding chaotic dynamics. So in particular, we know that if you choose x equal to 0 as your Poincaré section, then on the chaotic attractor, z also has to go through 0. So essentially, this allows you to just work with one-dimensional data on the attractor. And what I am excited, or what I'm enthused about that for, is because I am plotting for you in this figure in the middle essentially what your Poincaré mapping would look like, right? So this is the next iterate in the y variable against your current iterate. And what I love about that is essentially a one-hump mapping, right? This is sort of falling into Michael Feigenbaum's theory of these universality of these mappings. And so the first thing that you might try to do, and this is what I tried to do with the Cindy method, is try and fit a polynomial, in particular a quadratic function, to that data. Now, it looks like it should work near the bottom, near the sort of turnaround point for this thing. But if you look at the arms of that data, of that Poincaré section, they're just a little bit too straight, right? It just doesn't quite fit the mold of a quadratic function. So this is what we can do with the neural network. What I can do is I can deform those arms in such a way that I can fit this data onto a simple quadratic mapping. Again, I like polynomials, right? Polynomials are easy to work with. I spent like most of my undergrad working with them over and over. Why would I throw that skill set away now? So here's what I want to do. I want to compare the performance of the Cindy method against my conjugacy mapping. So this is what happened. I tried to learn a quadratic model using the Cindy method. And what I did is I transformed the data in such a way so that all you have to do to compare my results for the Cindy method to the conjugacy model is just look at that leading coefficient. Okay, so 3.67 against 3.96. Okay, so clearly the conjugacy model is giving a different quadratic mapping than the Cindy model is, but that doesn't say anything to which one might be better. Fortunately, I have turned both of these things into the very, very famous logistic mapping, right? Our prototypical one-hump mapping. This is the one that Feigenbaum originally started playing with and finding his very celebrated constant with. And we know a whole lot about that logistic function. In particular, we know that if you start changing that leading coefficient, you are going to drastically change the dynamics of the model. So what I'm plotting for you now is the period doubling bifurcation diagram. The parameter, the leading coefficient R, is on the horizontal axis. And then on the vertical axis, I'm plotting the attractor at each point. Now go ahead and put your finger on the computer screen and draw a straight line up from that 3.67 or so. And what I want you to notice is that the chaotic attractor for the Cindy model is disconnected. There are two disjoint components that make up this chaotic attractor. This is not good, right? Because if you look at the data from the Poincaré map in the top middle panel, that thing is not disconnected. And therefore, Cindy is not capturing everything here. Whereas if you look where the conjugacy model puts you, it puts you way further to the right. So the chaos is much more developed. And it's putting you in a parameter regime where you have a completely connected chaotic attractor. Okay, so that's sort of score one for the Cindy model, but it doesn't, it doesn't say everything. So what's another way that we could try and see who's doing a better job here? Well, what we could do is we could try and forecast the dynamics in the Poincaré section. So what I did is I just took a basic old Runge-Kutta scheme, your ODE 23 or something in MATLAB, and simulated up the Rössler system. And then I plotted as yellow squares the corresponding intersection of the system with the Poincaré section, x equal to 0. Then what I did is I took the same initial condition and I initialized the Cindy model, so just iterating forward under my Cindy model, to try and see how far ahead I can predict. And you can see that after about one iteration, this thing completely falls off and becomes a useless forecast. And again, that comes from the fact that it's just not doing a good job of fitting something to a quadratic system. This just isn't a quadratic mapping. Whereas what you could do instead is you could conjugate that data and then step it forward with the conjugacy model and simply undo the conjugacy on each one of those forecasted iterates. And that's what I'm plotting for you in the teal or the green, depending on your choice of color here. And you can see that this thing remains fairly accurate for about 6 or 7 iterates, right? So every one of these iterates is one full Lyapunov time. So you're going about 6 Lyapunov times into the future. That's pretty much as good as you can get when it comes to simulating a chaotic system. Sorry, I see there's another question. Okay, sorry. This is, I don't think that this is related. Okay, so then let's go ahead and turn to everybody's favorite toy system, and let's start looking at the Lorentz system. So in this case, you have something very, very similar. So this is a similarly 3-dimensional chaotic system, very, very simple, sort of prototypical. This is your butterfly chaos that everybody knows and loves, especially if you're coming from the model discovery community, where the Lorentz system shows up in almost every single paper that's written about model discovery. Now, in this case, I'm going to take my Poincaré section to be that sort of blue bar that connects these 2 unstable orbits at the middle of my lobe. So those orbits in this case are at z equal to 27. So this is essentially a piece of the z equal to 27 plane. Now, one of my favorite textbooks of all time is written by Guckenheimer and Holmes, and I have it on my bookshelf right beside me here. And if I was to go dig that out, I would find a very long chapter where Guckenheimer and Holmes go through the derivation of what a conjugate mapping for the Lorentz system should look like. And in this case, they come up with this form that I have for you on the board. So it's this sort of skew symmetric mapping in 2 variables. It's a 2-dimensional Poincaré section. So it's in 2 variables. It has this sort of symmetry requirement. That's number 1. And it has this jump discontinuity. That's number 2. So what I decided to do was I decided to sort of come up with the simplest form of a mapping that would sort of fit Guckenheimer and Holmes' description here. So fit these prescriptions, 1 and 2. And what I ended up coming up with is using the conjugacy system to discover this exact conjugate map that I have for you on the board. So you can see that it is a pretty sort of strange looking mapping. All of those decimals that you are seeing, those are learned by the neural network during the training process. So 2.52, that just came from the neural network. But what I really want you to focus on is the form of my system. What I did is I thought up a library of functions that is so minimal that it could capture nonlinear dynamics, but also fit the prescriptions from Guckenheimer and Holmes. So that 1 and 2 written right up above. And this is essentially what led me to this very, very simple right-hand side here. Now, The idea here is that I gave it very little to work with, and I let the neural network, the autoencoder, do the hard job of transforming the variables in such a way that it has to fit that mapping in the best way it does, or the best way it can. So again, you might have the criticism, you might say, well, I mean, it looks okay. It seems to sort of fit the prescriptions, but you know, what can I actually do with it? Is this thing actually useful, or does it just look pretty? Well, at the very beginning of the talk, I showed you a bunch of unstable periodic orbits from this Lorentz system. So the question is, how did I get them? I got them from this conjugate mapping. In fact, we have a way of classifying all of the unstable periodic orbits inside of this Lorentz system. It's just clarifying how many times you wrap around the left or the right lobe. So that gives you a symbolic way of describing everything in terms of L's and R's. And what I was able to do was sort of mine out the periodic points from that conjugate mapping, lift them back to the original Poincaré section, use a nice little shooting method to sort of initiate a root finding program in order to find these unstable periodic orbits. So I don't want to get too bogged down in the details there. What I do want you to look at is the last two columns of that table. In particular, it only takes me 7, 8, or potentially 9 sort of Newton iterates in order to converge to a solution. So it's very, very accurate. And the longest you're waiting for this to happen is about 20 seconds. Now, I pulled out much more than the periodic orbits that are listed there. I think I have probably about 30 of them at least. Essentially, the only limit here was my own patience. I just kind of got bored and didn't feel like it was worth pulling them out anymore at some point. But the idea here is this is extremely accurate and it is relatively simple. It's essentially just letting the neural network do all the hard work. I see that there's questions. Are they actually questions or are they discussion?
Yeah, like mostly comments, yeah.
Okay, should I?
But actually there was a question where he asked you whether he could enforce the discrete symmetries.
Predrag, this was yours, sorry? Do you want to ask? Do you want to turn it?
Yes, that was mine. Well, you know, can you enforce the symmetries into your conjugacy already? Because, you know that Poincaré map or fluid dynamic systems you're modeling has some discrete symmetries. Can you build them into this?
You can build them in by the choice of the library that you use for your conjugate mappings. In terms of the layers of the neural network, I know that there are people who are enforcing symmetries in the actual, in your sort of activation functions and in your weights of your neural networks. I haven't gone that far because I haven't necessitated much beyond, a really simple sort of sign flipping symmetry or something like that. But more complex symmetries, a dihedral symmetry, for example, that would probably, the training process would probably be greatly expedited if you could enforce that, or if you did enforce that into your actual network layers. It's just not something I've had to do yet.
Thanks.
Great. No, thank you. Thank you for the question as well.
I also have a question.
Sure.
It's this Guggenheimer and Holmes map has a very different form. It has infinite derivative at 0, and you of course don't have it, but you somehow achieve, as you say, great accuracy, which is
yeah. So what's happening there is essentially it is pushing. So in the Guggenheimer and Holmes, they have the region of validity is like -1 to 1 with that infinite derivative. What this does is it pulls you off of that that discontinuity at 0 a little bit. So maybe your discontinuity, maybe your region of validity for this discovered conjugate mapping is say -1 to -epsilon, and then epsilon up to 1. So what it does is it avoids that in some, just because I gave it this form. And of course, this is a sacrifice in accuracy, and you probably see
but that's interesting, because you have achieved a great accuracy, though you know that your map is not very accurate, which is
Well, you'll see the breakdown once you start looking for higher order Poincaré maps, right? Or sorry, for higher order periodic orbits, right? Because the higher order orbits are going to get closer and closer to the singularity, and that's where the accuracy breakdown. So if I looked for, say, maybe 100, period 100 unstable periodic orbit, that's probably where I'm going to see the issue. But the nice thing is these low order unstable periodic orbits, none of them really come close to the singularity. So I can avoid that. Does that make sense?
Yes, I got the point. Okay, so you're away from singularity, then it doesn't matter. Okay, I see.
Yeah. So thank you. Yeah. Thank you very much for pointing that out as well. Yeah. Okay. So then, let me show you another example here, and in particular, this is an example where I want to talk about this idea of sort of boiling out redundancies in your data, and in particular, searching for lower dimensional maps that might describe very high dimensional or complex phenomenon. And what I want to do is I want to focus on the Kuramoto Sivashinsky equation. So, typically, if you're going to do anything interesting with chaos, you're going to start with Lorentz, and then you're going to go up to Kuramoto Sivashinsky, right? This is a sort of tried, tested, and true formula for writing a great paper about chaotic systems. And so, if you want to work on maybe high dimensional data, Kuramoto Sivashinsky, provides itself as a nice arena where a lot is known. So there's a sort of a nice way of, or self-consistency here, nice checking. So in particular, I've got this partial differential equation up on the board for you here. This is a fourth order in space, first order in time partial differential equation. You can see that nonlinearity here is just coming from that quadratic term. So another appeal of the Kuramoto Sivashinsky equation is that it sort of has a similar nonlinearity to the Navier-Stokes equations. And so there's, at least some potential that, a complete understanding of Kuramoto Sivashinsky could lend itself well to something like much more complicated, like a fluid system. Now, the way that I'm going to analyze this, I'm not going to pretend that I'm analyzing a full partial differential equation. I'm going to follow in the footsteps of many people before me. And I'm going to introduce a Fourier or a Galerkin projection onto the odd Fourier modes. Now, this was not some arbitrary decision that I made. I didn't, just come up with this out of thin air in order to make my life simple. In fact, this has been done many, many, many times by many, many authors. And for example, I'm showing you a really, really simple system, a picture from a 2015 paper published in Chaos that actually did this. And what they showed is that the onset of chaos in this Kuramoto Sivashinsky equation comes from decreasing that hyperviscosity parameter nu in your system, where you sort of walk through these sequences of period doubling bifurcations until you eventually get to a chaotic system. Now, that picture that I'm showing you, this is not the first time in this talk that you've seen that picture, right? This is the same picture that I showed you a few slides ago when we talked about the Rössler system. And in particular, what I told you is that that system is, or that picture comes from a very universal phenomenon that was identified by Feigenbaum that really is sort of generated by, not high dimensional discretizations of partial differential equations, but very, very simple one-dimensional mappings. And so then what I decided to do was sort of following some other people's work here, I took a 14-mode discretization or a projection of this Kuramoto Sivashinsky equation, and that left me with a 13-dimensional Poincaré mapping, right? So it's a dimension lower coming from the transversality of the section. And then what you can do is you can use this as training data, you can feed it into the neural network, and you can project yourself down onto a one-dimensional attractor that completely describes that period doubling phenomenon that you're looking at in the bottom left corner. So in this case, what I do is I use the conjugacy to discover, the conjugacy neural network to discover a polynomial mapping, all I need is a quadratic order here. So you're identifying essentially a conjugacy with a logistic map. And I'm just giving you an example of one of the results. So for this value of nu, you can see that you are at a logistic map with about 3.96. It's very, very similar to what we saw a few slides ago with Rössler. It's very close to the fully developed onset of chaos in this logistic mapping. Now, again, what can you do with this, right? How do you know that this is actually useful? Well, again, logistic map, nice and easy. I can set up all kinds of little numerical routines to pull out the fixed points and the periodic orbits of this thing. And then what I can do is I can use the inverse of the conjugacy to lift those back up to the 13-dimensional Poincaré section. And then I can initiate my shooting technique. I can find those periodic orbits. And for example, I'm showing you in the top right corner here, the 10th Fourier mode against the first Fourier mode of this system. In white in the background is your chaotic attractor. Superimposed in blue is just one of those unstable periodic orbits that I was able to pull out. So again, in this case, the unstable periodic orbits, I think I pulled out maybe 20 of them or so. Again, you can get them out really, really fast, nice and quick and efficient. Again, the real limitation is my own attention span at this point and just trying to see if it's worth it to keep going or not. Okay, so in the interest of time, I'm going to skip over the last example here. So I do apologize for that. I'd be happy to talk with you a little bit more about that. But let me just wrap up because I see that there's some questions accumulating, right? So in the original work in this paper, we worked on Rössler, Lorenz, Kuramoto Sivashinsky, but we also have a bunch of other systems that we played with that illustrate various aspects of the method, right? The dimensionality reduction, the sort of forcing a specific form for coming from your library. Some of the things that I tried to highlight in this talk, but it's sort of more fleshed out in the paper, of course. Now, I mean, as I illustrated, there's a lot more to do with Kuramoto Sivashinsky, right? Kuramoto Sivashinsky gets much more complicated after you sort of go through this very simple logistic map chaos component. In particular, what I'm showing you on the right side here now, again, is the 10th Fourier mode against the first Fourier mode at a smaller value of nu. You can see that the chaotic attractor is much more complicated. But you can sort of play the same game. You can find in this case, a two-dimensional conjugate mapping. And I just pulled out one of the periodic orbits there that I've kind of been referring to as the bat, hopefully for obvious reasons. And then, as was alluded to by Predrag here, the real beauty of doing a lot of this stuff would be to try and get yourself towards working on fluid dynamics, where this could be a tremendously rewarding task. Now, I'm not saying that I am there yet, but of course, this would be really nice if I could get myself up there. And in particular, one question that I would love to be able to answer comes from my previous advisor, David Goluskin, who is a researcher in Rayleigh-Bernard convection, where there are a number of conjectures associated to these convection problems as to which orbits maximize heat transport. So, for example, many people think that it's probably going to be the steady state solutions, but it could potentially be these unstable periodic orbits. And so if you have a way of systematically pulling out these unstable periodic orbits, you have a way of systematically checking whether or not they're maximizing heat transport. And if they are, you could potentially implement a control algorithm to entrain the dynamics into these maximally heat transporting orbits. Okay. So thank you very much for your attention. I appreciate everybody coming today. Again, it's important to note that the research doesn't happen in a vacuum. I'm not trying to say that I'm the sole contributor to this project. Of course, it was supervised by Steve Brunton and Nathan Coots. And then some of the later work that I skipped over with the Kuramoto Sivashinsky was helped out with some great undergraduate students. So Jay, June, and Amelia and Carter. If you do see this, you guys did an excellent job with all of this. So thank you very much.
Okay, thank you very much. Any questions or comments?
I think I see some in the chat.
Yeah, if I can ask one. So you were contrasting your method with Cindy, but then I thought you said you are actually using Cindy still to fit your polynomials.
Sorry, can you say that again? You're talking about this process in here.
Yeah, so I thought you were using Cindy to fit G.
Yeah, so essentially what you're doing is you expand G as a library of in a library of functions, and then during the training process you are identifying the coefficients in front of those as trainable network parameters. So it's not a perfect Cindy process because I'm not doing the sparsification step.
But if you have a library, then you have to do some sparsification.
Yeah.
Otherwise you'd have. So I don't understand why you're saying it's not Cindy.
Well, so for many of the examples that I showed you, you have a target for what the mapping is going to be, right? So for example, with my Rössler system, I wanted to target the logistic mapping.
Okay, so you do the sparsification.
Yeah, so this is, I'm glad that you asked this question though, because this is a sticking point going forward, right? So, if I give you just any random chaotic data, right, you're sort of faced again with the problem of what to put in the library, and you can implement a Cindy type thing where, every certain number of epochs during the training process, you can perform a sparsification procedure, much like in the Cindy method. And this is something that Steve Brunton and Nathan Coots did with a former PhD student, Kathleen Champion.
Thanks.
So thanks for the figure, which is on the screen right now, because it makes lots of sense when you phrase it this way. And, I don't have problems with differentiability or not, because you're using polynomial conjugacies to get the polynomial maps. It's perfectly fine. I mean, nothing mathematically tricky is going to happen there. It's only if you insist that you get a piecewise linear map that things will go bananas, but this probably is okay. So thanks, Emil. I like that.
Yeah, I do want to emphasize, because sometimes I get pushback on this. I am not trying to create theorems here, right? I'm trying to use mathematical theory to create approximations of these systems, right? Doing the best that I can with the numerical framework. And so there's nothing, so Predrag, this is besides your point, this is for everybody, right? I'm not saying this is the conjugate system of Lorentz, right? I'm just saying this is the one that I was able to find, and it turned out to work very, very well. That's all that is trying to be said here, right? There's no theorem that I think is hiding underneath this.
So if nobody's asking question, I have three questions. One is when you have continuous symmetries, when you have discrete symmetries, you have to take care of them. And presumably you do this by using the library being discretely symmetric polynomials. When you have continuous symmetries, you have to take care of them. And, the reason why you're doing your Kuramoto Sivashinsky invariant subspace is to avoid looking at that. So that's one comment where you have and I'll have another one, and then I'll shut up. The next one is, this is conjugacy for the maps. Do you have conjugacies for the flows, for the differential flows?
Yeah. So let me start with the first part of that. So for continuous symmetries, actually, I've been working with Barak, your former student, Predrag, using his symmetry reduction techniques in order to get us into a symmetry reduced space. And so that was something that I skipped over, but we started playing with. So in one of your former papers with him, you were looking at the onset of chaos coming from this breakdown from an invariant tori coming from a Naimark-Sacker bifurcation. And so the proof of concept that we played with there was using those symmetry reduction techniques in order to find a projection onto the center manifold and find, your governing map for just this Naimark-Sacker bifurcation. So certainly there's a lot of potential there when you have continuous symmetries. It's going to be much more involved, but it seems that one possibility is using these symmetry reduction techniques. Now I managed to talk so long that I forgot your second question. I apologize.
Oh, the second question is, this is conjugacies for the maps, but usually
Yes.
they're given flows. So, do you have the same thing for the flows?
Yeah, so in theory, there's nothing stopping one from doing it. So as I mentioned, there was that previous paper by Champion, Brunton, and Coots, where they did something sort of similar to this, primarily for continuous flows. But again, I think that there was an implicit sort of discretization of the data underneath. So I'm not sure. So the answer is yes, of course. I mean, I don't see any reason why this wouldn't work for flows. It's just that I haven't, this is the first I've thought about it. So I appreciate you bringing it up. For me, it was most of this stemmed from my issues with Cindy and my sort of lack of creativity for finding these, what should be in my library, and then sort of jumping to say, okay, well, let the neural network do the job here. So of course, yeah, these continuous time systems are certainly approachable, I suspect, through similar methods.
All right. Any other questions?
If there is time, I have a couple, but if there is no time, no problem. I understand.
There is time. Yeah, I think he has 5 minutes, maybe. Yeah.
Okay.
Yeah.
Okay. So the first question is quite technical, while the second one is more philosophical. So I hope that on average will be at least almost an interesting question.
My wife is a philosopher. Maybe I should call her in for the second one then.
Okay, so the first one is about Cindy. The simple model. So you basically told that you first do the least squares, and then you do the thresholding in order to promote the sparsity, right?
Yeah.
In order to promote sparsity, the first thing that I would come up with should be try to insert some L1 regularization on the coefficients. So is there any, I don't know, computation unfeasibility in doing that?
Yeah. So that's essentially the lasso regression, right? Or lasso regression.
That's right, yeah.
Yeah. So both of them are just different ways of trying to approximate L0 regression, right? The original Cindy paper does compare itself to lasso. It's very comparable. It sort of functions very, very similarly. I guess the only difference is that lasso has the potential of giving you small coefficients, whereas this one just zeroes things out immediately, right? It says but there is a nice aspect to this, because once you zero something out, then you can repeat the process. You have this whittling of the library that's happening here. And so the idea is that if you started with a huge library, every function you've ever encountered in your entire life, right? At every single step, it's going to get smaller and smaller and smaller. Now, you could, in theory, do that with lasso as well. You would essentially be, doing exactly the same thing as the Cindy method, right? You run lasso, say, okay, this is small, I probably don't need this. Run it again. This is small, I don't need this. So essentially, it sort of turns into the same process.
Okay. And the second question is, I think, related to the next slide, where you have the autoencoder. No, the next one.
Oh, yeah.
Okay,
yeah.
This one. Okay, this is the question now is more philosophical. So if I have something very complicated, my natural intuition is that maybe if I lift it in a higher dimension, it becomes easier. For instance, the knots. So knots in R3 are very complicated, but if I lift a knot in R4, it becomes S1, right? Or are all trivial, the knots in R4. So if I have a very complicated dynamics in some dimension, it could make sense in principle to lift it in some higher dimension in order to hope to have a simpler dynamics.
Yeah, I mean, that's sort of the principle of Koopman theory, right? That's exactly what the trade-off with Koopman is doing, right? You lift yourself, unfortunately, into an infinite dimensional space and things become linear. So yeah, I completely agree with that. my personal preference is keep things small. I'd rather small and nonlinear than large and, you know,
linear,
almost linear. But that's a personal preference of my own. And so, yeah, I mean, I completely agree with this. And I suspect that, you know, there are many situations where that would be a much better approach. For the examples that I showed you in this, in here, it's, you know, it was all geared to be sort of lower dimensional and looking at, because that's sort of the world that I came at it from. But I agree. I mean, yeah, especially things like where you have these knotted manifolds or something like that, then lifting them up to get rid of knots, for example, would be, you know, the best thing to do. Certainly.
Okay.
Yeah.
Thank you so much.
Just haven't encountered the right problem yet.
Thank you so much. Very, very nice talk.
Thank you very much. I appreciate it.
Okay, then I think Jason needs to teach now, so I think he doesn't have much time.
May I make a comment? Since you mentioned Bernard convection, Rayleigh-Bernard, it looks like to me an organized turbulence as opposed to turbulence which is not organized. And will it be interesting to look at that too?
I'm not sure I can comment on too much of that. So I'm not an expert in turbulence, so I don't know what organized versus disorganized even means. So.
Well, you have temperature difference that is driving turbulence in fluid that is contained in some container. So you get those cells that are repeating themselves all the time. However, turbulence can become wilder. I want to ask another question then, and this is more curiosity. If I look at the Lorentz system, and if I'll take a closer look at the Rössler, but in Lorentz, it's very clear that the two centers are basically very close, okay? At the bottom, the intersection of the orbits is close to become distance 0. The centers are a bit far away, but they're still kind of attached. What if I look at the system that the two red dots will be at distance, and I will dare saying at far distance? Has anybody looked at that?
I mean, you could always just rescale your system to bring them close together, right? Through a linear scaling.
Yeah, but if you want to contract them, so it's like something happened within, you know, they could be also not only touching, they could be overlapping. Okay, if I shorten that distance between the centers, if I have a way to do that, then they become one. And on the other hand, if I increase the distance, if I stretch the distance between the two red dots, I'm, you know, maybe up to new stuff.
Yeah, I'm not sure. I can't really comment on it because I haven't tried it. But if you can send me, if you have a reference that you would like to send.
No, it's not a reference. It's just my intuition at the moment.
Okay. Well, I mean, if you feel free to reach out to me by email if you'd like to.
Okay, I will. I will. Yeah. Thank you very much for a beautiful talk.
Thank you. Thank you.
Okay, so I think Jason has to go to teach.
Yeah, my students are going to be happy if I show up late. So I do apologize.
Okay, thanks everyone, and thanks Jason again for the talk. Yeah. Okay, bye-bye.
Thank you very much for everybody for coming. Thank you.